Now, yes. Okay, sorry. So, it's a bit too close. Lecture number 3. So today we will be moving somewhat to smaller redshift, so closer to us, right? The first lecture, intensity mapping, the post-ionization era, focusing in particular at high redshift, even though, you know, the actual measurement, the few measurements that we have are below redshift 1. Yesterday, the intergalactic medium, more or less between redshift 2 and 6, let's say, and today galaxies. So, and the point that I want to make here is to address the galaxy clustering, both as a dynamical probe of structure formation and as a geometrical probe, right? So, to see more or less, to start from the building blocks and to go to the final measurement, the state of the art in terms, again, fundamental physics. So here there are a few references that you might want to look at in case you're interested, but of course there are many others. And so I believe, you know, that the breakthrough in the last years has been these fabulous experiments, the SDSS 3, then which is BOSS, and now we had eBOSS, an extension of BOSS, and now we have DAISY, and there are also people, of course, in the audience working several aspects of these observations. Now, it's a wonderful telescope, and the point that these slides want to make is that here galaxies are really tiny dots, and these stripes that you see, they are due to the survey geometry, basically to the way in which you are looking at the sky. And if you zoom in, you see that these galaxies, they do have structures, and inside galaxies, there are also other galaxies, right? Sabelos, dwarf galaxies, maybe. And so, you know, it's we will be interested in the somewhat large-scale properties of galaxies, but do remind yourself that these have structures, right? There are underneath, inside them, there is some structures. And so, BOSS in a nutshell, so this is the telescope in New Mexico, very close to White Sands, so not... I would say not an ideal place to place an instrument, right? Because the white sand is really over there, so it maybe looks also not very clear, the sky, but nevertheless, it's very efficient effort in which this is fiber fed, so they have these plates that you might have seen. They drill holes in the plates and they put fibers and they collect over a night several of these plates. They collect lights really from objects in the sky. So you do lots of work to select objects a priori before starting the instrument, before starting the survey. But then when you know where to look at, things go pretty fast, right? And so this is what they surveyed. So this is, you see, several colors represent several tracers, quasars, Lyman alpha, nearby galaxies, luminous red galaxies, and they give different names. And different colors, in this case, also you see all the objects that they're tracing, and then they look at the correlation function, and in all of them you see a bump, so effectively they are tracing tomographically the BAO peak at different redshifts. And this is, of course, very important in terms of geometry of the universe. So out of this network of points, right, filaments, structures that you see here, there are the number of questions that you can ask is really huge, right? And so, for example, here you might wonder what to do. Well, the first thing, you can look at the power spectrum and get an idea of omega matter, omega baryon parameters. Then you can look, for example, at the angular projected clustering scale, both for the BAO and voids, the radial projected clustering scale, line of sight dependent clustering, which is affected by redshift space distortion, which we will use to perform cosmology, to study, for example, modification of gravity models, neutrino masses, primordial non-Gaussianity, the same question that you might ask yourself if you look at the CMB. You can also look, you know, at the bispectrum and the scale-dependent bias in this by studying the clustering pattern of these galaxies. Higher order statistics, by spectrum, you can do lots of astrophysics, small-scale modified gravity, and then also you can ask somewhat more basic questions like isotropy, homogeneity. Is there a dipole in the structure, some preferred direction? And that may hint, of course, of fundamental physics. So I think that the very basic thing that you might look at is the correlation function. Right, so this is a correlation function for matter. So what you do is you average out over the sample, right? You can move in different part of your sample. Suppose this is the matter field, the density contrast at point 1 and point 2, and for homogeneity isotropy, this will depend only on the relative distance between these two, and this, of course, sets the relationship between the power spectrum and the correlation function, which is one of the Fourier transform of the other. Okay, this is in terms of matter, but we are dealing with galaxies which are tracers of the underlying dark matter. So we are dealing with points, and so what you can cast this very same quantity in these terms in terms of probability of finding a galaxy once you sit on top of a galaxy at a given distance xi from you, right? And this can be cast in terms of excess probability with respect to, let's say, a random or uniform distribution like this. And so if you now are counting neighbors around you, you can get very easily this relationship here, just from this. And so this is the number of neighbors in a given DR, in a given radial shell. And if you look at this and then you integrate this, you can clearly see that this quantity here, 1 plus c, is also can be interpreted physically as the average mean density profile around galaxies, right? You sit on a galaxy, you calculate the profile, then you sit on another galaxy, then you average this over all the galaxies, and this is what you get, the correlation function. So it has this twofold meaning of excess probability and also average density profile. Here things looks nice, they are isotropic, right? But in reality, they are not. In reality, they are not, because there is a preferred direction, which is the one that we are looking things at, which is along your line of sight. And basically this correlation function, which is isotropic in real space, gets modified by several effects due to the fact that you are observing things in Redshift space, and in reality, this correlation function will be squashed in some regime, even can get down to, a collapsing. And also, at very small scale, you have these so-called fingers of God effects in which the galaxies, are really overshooting each other somehow in the innermost part of galaxy cluster. And you have an elongation at small scales, a squashing at somewhat large scales in this direction, and this is the intermediate regime between these two cases, right? And here you see a simulation, real space, Redshift space. You can really see that they look somewhat different. And so we will be using Redshift space to gather even more information. And so how to do this? Well, if you look at textbooks, physics, cosmology, physical cosmology textbook, this is the relationship between Redshift space over density of tracers with respect to the real space. It looks somewhat complicated, but in reality it's not, because you put yourself in a plane parallel approximation. It means that these objects will be very far from you, right? Not very close. And then you cast the overdensity contrast in Fourier space and in Redshift space in these terms, where this is the bias, this is the Redshift space distortion term, and this is the projection of the wave number along the line of sight, which is chosen to be the z-axis in this case. And so once at this point, if you remember the power spectrum definition, you use this, you plug this in, and you find interesting relationship between the monopole of the power spectrum in Redshift space and its real space counterpart, where there are these beta terms appearing, even as a power of 2, and this direction between the quadrupole and the real space and the hexadecapole in the real space. So effectively, with Redshift space, physically we are opening another coordinate, but the relationship between this coordinate and real space quantity is somewhat easy to interpret, at least in linear theory. And if you plug in reasonable number for this beta, which depends on the bias on the tracer and the cosmology, you will see that this power spectrum is typically enhanced. And so Redshift space distortion is not really washing out primordial information, but is really increasing its value with respect to the real case. Okay? And so this is the so-called Kaiser formula, because it was pointed out by Nick Kaiser 40 years ago, and is at least in linear theory, it's casted in this way, where there is this deterministic bias, this Redshift space distortion term, which depends, of course, on F. F here will depend on cosmology, right? F is the linear growth, the growth of structure in linear theory with respect to the logarithm of the scale factor, right? So it's something connected to the growth of structure, but also connected to parameters of your cosmological models, like omega matter. So people knew this thing for a long time, but then at the end, of course, they were not just happy with linear theory, right? Because if you if you plug if you observe this and you overplot some linear theory power spectrum with the equation that I showed before, you see that things work pretty well at large scale. It means small wave numbers, but then at some point, at k of 0.1, 0.2, the linear theory doesn't really work, which is this dotted line. And the nonlinear prescription that they have in this paper also doesn't work. So you might wonder, you want to fit things better, and that's why you want to model, for example, this bias function a bit better. Right? And this is one of the models, which is why it's still used, I would say, by the community, in which you modify the linear bias by this extra function here, which is somewhat phenomenological and could be calibrated with MOX, but it's something that people realized very early on, right? That different galaxies have different bias in terms of amplitude, bilinear, but also in terms of shape, which can be up to some wave number described by simple, somewhat phenomenological functions. And once you want to get out, for example, neutrino mass, you would like, for example, to marginalize over this Q&A to be sure of your result. And this is again a paper by Percival, something like 10 years ago, in which you see really that you split the galaxies into different ranges of luminosities. These are red galaxies, blue galaxies, and you see really that only at large scales the bias gets flat and well behaved somehow, but then very soon it gets this scale dependence, which is different depending on the galaxies you are looking at. And we will see maybe what's the reason for that. So then, of course, you want to somehow understand this bias in terms of more fundamental physical quantities, right? And one possibility is offered to us by two pillars of structure formation. One is basically the press-Schechter, formalism Schechter-Thorme, in which you describe the mass function of the halos, right? And the halos for us are galaxies. And it's in this, it can be casted in this way in terms of overdensity of let's say, of halos, or let's say patches of the universes, right? Regions of the universe. And this S is the variance of your field, which is related to the power spectrum, right? We know this very well. And this theory is so powerful because it gives us also conditional probability that a halo of a given mass M1 will end up at a later time in another halo, typically bigger, of larger mass M0. And so we know mathematically very well this thing, this theory, let's say, and we can use it now to get the bias. And so you interpret, let's say, M0 could be a halo, but could also be a region which later on will undergo collapse, right? And so if you work out the numbers here, where the key quantity is this nu, which is delta over the variance of your field. It's a number that typically is a quantity that typically appears in peak theories, right? In which you have this smooth density perturbation, and on top of the peaks, you will have halos and thereby galaxies. So you aim to describe this statistically. You can work out this overdensity of halos, and it's easy to see that if you drop this higher order term, then there is this simple relationship between the overdensity of the halo and the underlying dark matter density, let's say. And this bias will depend on what? Will depend on the growth factor of your cosmological model, and will depend on this new one, which in turn depends on the power spectrum. So the bottom line of this slide is that if you have a power spectrum linear, it's very easy to get the bias of these halos. You just calculate the variance, you plug it in these numbers, and it works very well just with one integral, let's say. So the point is now, is this enough? Well, let's go to this slide. Now we have a numerical experiment, a simulation, in which I select the halos of masses 10 to the 11, the only halos for which 20% of halos, sorry, with the latest half mass assembly in this 30 megaparsec thick slide. It means that they have accreted their half of their mass recently, let's say, okay? At very recent times, yes. And then we compare this with the same, let's say, halos, the same halos of the same mass, but which have accreted their mass at very early time. So these halos are somewhat passive now, but in the past they were accreting a lot. So these two families, they have the same mass, but if you look at the pattern, they are radically different, right? In this case, you have something a bit smoother. In this case, it's clearly more biased, more clustered. So now you take the bias of this as a function of mass. This is mass over, I don't know, maybe stellar mass, yes. And you see that the bias is very different. The red is this one, the earliest, this is the latest. And here they are in agreement. For very big objects, they trace the underlying same structure. So if you pick up the biggest objects here, you just select those, it works fine. But for the 10 to the 11 masses that we just considered, which is probably somewhat here, the bias are really different, okay, by factor 2. So of course, if you now you go to a simulator, you say, okay, give me the mass of the halo, and then we'll paint galaxies according to the mass of the halo. This thing will not work, right? Because it's a higher order, very important effect, which takes into account the formation time of your galaxy. This is why halo occupation distribution approaches, which are very widely used by the community, including myself, to do mocks, let's say, to compare with data, to make a fast pipeline of simulation, then they suffer of this limitation, which can be somewhat, let's say, relieved if you refine your model, right? For example, you can ask, okay, now we'll populate halos according also to the formation time, to the concentration, to the spin of the halo, to the shape of the halo, and then there are also these other quantities that are very important physically that are even, more sophisticated. And at the end of the day, if you do like this, you will have many more parameters describing the bias, right? Not just the mass, like in the previous slide, linear theory. You can have the spin, you can have many different things, but your model gets more physical. So people did that also to interpret the signal like this one. So this is a real signal, which is the color, let's say, the colorful part of the plot. And these black lines, I believe, are the theoretical model. What is this? The color indicates the third coordinate, which is the value of the correlation function. This S is the Redshift space coordinate along the Laguna site in the perpendicular direction. So it means that here we will have many galaxies, and here fewer, right? And you see that here we do have structures in this. What do we have? We have an enhancement in this ring, which is the so-called baryonic acoustic oscillation, which of course depends on the as parallel as perpendicular. Here you see is somewhat more galaxies compared to here. You have the fingers of God effects down here, very small scales, but important maybe for several reasons. And then here you have also a squashing, which is again an effect predicted by the theoretical model. And suppose you get, in order to have the theoretical model passing through these colorful contours, you need to do the so-called Alcol-Paczynski test. You need to pick up your cosmological model right, because if you don't, you don't agree with the data. So this is the so-called, the Alcol-Paczynski effect exploits the fact that you have to choose a cosmology to convert from between, let's say, redshift and angles to actual redshift space coordinate. So what is the baryonic acoustic oscillation? Well, it's the same things that we saw before in the CMB, right? This is taken from Martin White website. And then there are many papers, of course, on this. So remind you what I told you before. This is a perturbation in the initial conditions, let's say, of our toy model. And so this is effectively a third coordinate, which comes towards you, in which you have a concentration of fluid. And the fluid, again, you can look at this as an average density profile. And as I told you before, profile of this energy density is the correlation function, right? Something like several giga-years later. And that the point is this. But here we are at the CMB, let's say. These are tracing each other fairly well. They are the same fluid. The mass profile would put a perturbation like this, slightly displaced from the center. And then, you let this evolve with physics, linear physics. There's nothing more than linear physics here. The same physics over the CMB. They are the same, they expand, right? They move together outwards. And what is causing this is the radiation pressure. And then this expansion continues for about 10 to the 5 years. But at some point, radiation is somewhat faster, and the baryon starts to lag behind. And the universe, why is that? Because the universe basically allows the formation of neutral hydrogens, recombination. And so the two, they're not tracing each other anymore, but this kind of behavior continues, right? Continues, the photons continue to stream away. and the baryons, they don't have anymore the radiation pressure. They are behind. And then at some point, this thing goes on till recent times the radiation is not important anymore. It fades away very quickly. But this kind of ring, which is the leftover of the decoupling, is still present, right? And after that, gravity keeps working. And the final configuration of this correlation function, of this profile, of this wave expanding, will be something like this, in which you have basically this ring here, this BAO peak at a given position predicted by the model that you want to look after in the data, right? That's what we are really after. It's the same physics of the CMB, but something like 10 gigayears later. Of course, in the CMB, these perturbations are over the unity, right? They are very prominent. In the large-scale structure, it's not like that. They will be suppressed, right? Because it's a completely different regime, and the matter is now this galaxy will be tracing the matter and not, let's say, the fluid as in the CMB. And so people started to investigate this thing, especially, I would say, Eisenstein, and so they look at the correlation function in simulations. You can look at this, you can implement this at redshift 49 and study its redshift evolution. And so you see that the higher the redshift, the more prominent the peak is. The lower the redshift, the things, the peak is washed away. And so the first question is, by redshift 0, where we have most of the galaxies, maybe we don't have a peak anymore. No, actually we do have a peak, also at redshift 0. And people said, okay, but we kind of want to have a sharper peak. It's easier to identify a sharper peak. And so what they did, they invented some techniques to undo the nonlinearities in these peaks, that they cancel the peak, and kind of go back and sharpen the peak a little bit to measure it better, right? And this thing goes... It's a kind of, very important topic, of course, because you can invent your own technique. So this is the correlation function. This is, again, simulations. And this is the power spectrum. The position of the peak in the power spectrum will appear as a set of wiggles. We know this. And again, in the power spectrum, the nonlinearities are washing out the small scales somewhat with redshift. And the lower the redshift, the more it will be washed out this frequency pattern that is related, of course, to the position of the peak. And now you can ask yourself, what should I do? Should I look at the correlation function? Should I look at this? It's a bit like the question that some of you asked to Fabio in the very first lecture. When you're looking to these features in the power spectrum, what should I look at? Depends on the amplitude, depends on the frequency. And so it depends a bit on your experiment. But the first paper, they were focusing on this because they thought, rightly so, that it's easier to identify this rather than looking at, peaks which are smeared out. So the height of the peak changed with respect to the different normalization of power spectrum. And this is what happened to the position of the peak in terms of error when you change the power spectrum amplitude. So in principle, it's case like this, but there is a second order effect, which is this one here, which depends on the quadruple of the correlation function, so integral of power spectra. And it depends also on the sigma square V, which is a term describing the bulk velocities of this galaxy. So if you think about if these galaxies are like dark matter particles, you set the initial conditions, and typically you do this with Zeldovich approximation. You create a displacement which is related to the power spectrum. This displacement is related to the potential. And so eventually you can describe nonlinearities with Zeldovich, which is the simplest approximation. And then you can also undo this thing back and sharpen the peak. And a way to describe this displacement of galaxies, you're not interested in a galaxy on a galaxy by galaxy basis. You're interested in shells at the scales of the BAO peak. Luckily, the scale is large, it's 100 megaparsecs. So what you do is you average out the behavior of galaxies by considering them as a bulk flow motion, particles moving with their initial velocities at a given scale. Right? That's what this term here. So things are a bit complicated, but maybe not, because there are established algorithms in the literature to do this for you with just few Fourier transform. This is a paper of a student of mine who is now in Zurich, and you see this is the algorithm that outlines what to do in order to undo this nonlinearity, and it's very simple, right? I played myself with this equation when I was a student. You just displace things with Zeldovich. You compute the overdensity, okay, basically with this simple equation. This is the potential, which is displacement field. You do things, typically do things in in Fourier space because are faster. Then you filter the nonlinearities. Then you get the displaced field. And then basically you go back. It depends if you are in Redshift space or real space. It's a bit more complicated. But at the end of the day, you reconstruct a more linear field out of this nonlinear field. Right? And this sharpened the peaks, and it changed a bit the shape of the BAO. In this paper, it's interesting. Why did I put this? Because we applied these techniques to pixels rather than galaxies. Here we have galaxies, but in density mappings you do have pixel. What can you do with pixel? You clearly cannot move pixel, right? You have to change a bit the intensity in each pixel to recover the BAO with intensity mapping. The algorithm for pixels becomes even simpler and even faster, right? So, a theoretical framework a bit more, correlation function can be estimated like this instead. People also work with the correlation function. What you do, you set two catalogs, one with the actual data and one with set of random distribution of galaxies. And this random is basically to take pairs in the random catalog. This DD is the pairs of galaxies at a given R separation in the real data. And this you take one in the random and one in the real data. And you build up this estimator of the correlation function, which is very famous, called Landis-Dalai. It's very famous because among the different estimators, this you can calculate analytically. It returns to you the minimum variance. It means that you will be measuring the error in this quantity much more precisely with this in terms of excess probability with respect to another estimator which has just, for example, DD over RR. So then you can decompose this in multiples, or you can do things, you can work things out in Fourier space with the power spectrum, Redshift space distortion, finger of God, nonlinear power spectrum, and again, these analyses are focuses on the wiggles, and so you want a description of the wiggles, and where are nonlinearities hidden in this? They're hidden in this sigma. Sigma is a way of filtering or smoothing the signal as nonlinearities will do, right? And here you smooth it at the finger of God scale, very small. But here you smooth the Gaussian damping of the BAO because the shape of the BAO will be damped in two different ways across and along the line of sight with these sigma terms. And so this gets modified, right? And so you want to calibrate this sigma with simulations, but eventually the data themselves, if you are interested in the shape, will tell you what these numbers are, of course. So anyway, let's make a step back, just geometry only. Position of the peak will allow to measure angular diameter distances, Hubble distances, or also combination of the two, right? In this case, you will have this so-called volume distance. If you don't want to, let's say, if you are not sensitive enough to this both coordinates, you can average things out and get this distance here, as in the first paper was shown. So things get very technical. People have been working on this for many times, for many, many years. So it's more, now you have to address very well with your systematic error, your statistical error. You have to disentangle the two. A very big problem is the window function. The window function is where you observe things. So it's not a trivial quantity. It's actually the most complex quantity you might think of because it's not just a geometrical quantity. It's not I have data there, I don't have there, here I put the window function to 0, there to 1. No, the window function encodes all the possible systematic effects that you also have in your instrument, right? Which can be, seeing, dust, things like this. They are all encoded in a random catalog which samples the window function, right? That's a bit the idea. It's a bit complicated. So the window function, selection function are the most important quantity to extract this information. At the end, the computation of the correlation function itself is easy. It's easy. It's fast, easy. There are codes available. But in order to characterize the window and selection function is somewhat more difficult. And so people, they develop codes which might be fast or a bit slow to get the correlation function, mocks. You put realistic mocks with systematic effects, get the covariance matrix correct, improving the reconstruction techniques. There are many techniques to reconstruct, not just the one that I showed before, based on also, Wiener filtering, for example, or other things. And the state of the art is anyway still provided by BOSS. There is Alam 18, Vargas Mañana 18, now more recent paper, 2020. And you can look at this, you can ask me later. But basically, the point that I want to make is that this survey of galaxy, if you look at the distribution of galaxies that have been used, is very different, right? This is the end of this edge. So effectively, by having this different the n of dz, you are filtering your signal to different redshift. It's like having a window function in the radial coordinate. And so this is a very important test of the model, because suppose you get BAO values wrongly between two data sets, right? Not consistent with each other, could be new physics or could be systematics. So this is the dndz. And the analysis now has been performed both in real space and in Fourier space, right? And so this is really remarkable. What you see here in Fourier space, you see the wiggliness of the power spectrum, right? This is the monopole with respect to a monopole which is smooth. You really see these frequencies. This is at the level of the quadruple, different redshift beam, and also in real space. And so this is the power spectrum reconstructed in Fourier space. This is, of course, a model because it looks fairly smooth. And this is the correlation function. Of course, the two, they are related to each other via, say, Fourier transform. But the way in which people, got to this final result, it took about, 10 years of science to go back there. In terms of cosmological parameters, what you see here is the h of z and dm of z is the angular distance, I believe. For different, let's say, approaches, different techniques. So this is the Planck, which is very tight, and this is one Fourier space, one is real space, the other one exploits in a kind of different way the splitting in the redshift coordinate with these mu wedges. And more or less, the point that we want to make here, they all agree with each other, right? They are all on top of each other, and they have a consensus BAO measurements, which is really the combination of the two, somewhat with some covariance, I guess, and then it agrees with Planck very, very well. Okay, so it's really Planck and BAO, they are in love with each other. It's really a chain that you cannot break, and typically now, when you advocate, for example, solution of H0 tension in the low redshift universe by having phantom dark energy, W is smaller than -1, you break this nice wedding, and you try to insert inconsistency that either BAO or Planck do not want. Okay, so it's really remarkable that this same physics can be tested something like 13 gigayears after the last scattering surface. Maybe I can skip this. Let me also skip this. Let me go to this one. Right, this is the final numbers. You see that this is a few years ago. The value of the statistical error is still, I would say, a bit larger than systematic error. And so I believe that with DAISY we will go down this, and this one beating this down will be somewhat more difficult, right? Because you need to work really on the systematics, much better level. But the statistical error can improve, and indeed with DAISY, it is planned that these numbers here, this value of H and the M will be much more, let's say, better measured. And this is in the full, let's say, long lever arm, in which you have also the Lyman alpha BAO, the present status, ALAM 2022 or 21 or 20, I don't recall now exactly. This is the geometric measurement. This is F sigma 8, which is basically the measurement of the redshift space distortion. And so you see this is the model that fits the data, and these are the values that you get out of this galaxy clustering pattern. So let's ask ourselves about new physics. This is the thing that I just said, right? Paper Aubor et al. 2015, so it might not be the latest data release. So what is this? This is DH and DAM. These colors refers to the dark energy, let's say, equation of state, W parameter. The bluer you are, you will be pushing this part of the parameter space, right? And so these are the chains. And this is what you get from baryonic acoustic oscillation from galaxy clustering. And what you see is that the two, they kind of agree with each other only when this number gets to, let's say, closer to the -1. If you go to -2, -1.5, you tend to evade the BAO, right? You are far from BAO. And I believe that this line here is Planck. For the Lyman alpha BAO, as I showed yesterday, this is the Lyman alpha BAO, this is the Planck value. And so you see that you are more in agreement with the Lyman alpha BAO when you are maybe in this, for this color here, I guess, right? If I didn't, if I'm not mistaken. F sigma 8, again, another compilation of F sigma 8 values from clustering. So maybe there is a general tendency to have more scatter point underneath rather than on top of this envelope, which is the Planck results. but probably this is not very statistically significant, right, I would say. And so again, you can use these data points to test modified gravity scenarios. This reiterates the same point. Let me maybe skip this. Maybe this is more recent. What is this? This is W versus omega k. So in this case, we let both the curvature of the universe vary and W. And so you see that Planck plus supernovae doesn't tell much. We know the reason for this, right? Because of the general internet of the CMB. But once you try to apply BAO, the full shape, then you get in this region of the parameter space. You are pulled towards this part of the parameter space in which you are maybe consistent with W minus 1, with some error, and with zero curvature. So these are really important tests that you can do also in the WA, W0 plane. If you want to follow this with dark energy, which an extra, let's say, WA term, you are, again, when you combine Planck and BAO, you are pushed toward this part of the parameter space. And these are very important tests because if you are looking for new physics, at some point you want a part of your data space, of your data sample, to drive you out, right, from the consensus models. We really hope that in the next few years we'll be in such a situation. This is if you allow some Redshift dependence of F sigma 8. In this way, Z pivot is measured by the data, is given to you as a pivot by the data. You let an amplitude free and an evolution free, and you ask yourself again, this is plain lambda CDM, and 1 sigma, 2 sigma, you don't find deviation. So it reiterates a bit the thing that I was saying, are the points that are scattered a bit below the Planck consistent with lambda CDM? The answer is yes. So it's really, sometimes doing chi by eye is difficult. So since we heard about also the sigma 8 tension, let me show you in a recent paper, I feel, even in which they used the effective field theory of the large-scale structure. They have these data points. It's a completely independent analysis of the same data, more or less. And what you see here is what does change in terms of model with respect to the data once you let this sigma 8 vary between 0.5 and 0.8. And you see that the change is small, right? It's relatively small. It gets washed out here because of nonlinearities and because of interplay with the window function, I would say. This is the monopole and the quadrupole, two different colors. So the point that I want to make here is that, when we ask ourselves what are the sigma 8 values that this data are suggesting to us, this is really driven by a handful of data points in this part of the parameter space. K 0.05, we are a redshift 0.6. If you can really look at the chi-square, and you see it grows a lot for these large-scale points, and then it somewhat flattens out and it grows a bit less. So if you ask yourself, I want to measure sigma 8 from galaxies, those are the points you really need to focus on, right? In the sense that you can develop your theoretical models. Perturbation theory here works fairly well, and to investigate really how these points compare with the data, and hopefully in the near future we will get much smaller error bars here. Let me skip this. Curvature, I just said something. Oh, so the other, opening of the parameter space is when you have dark energy or neutrinos. This is only dark energy, and this is only neutrino mass, different. And so again, you see the beauty of these experiments in which you have CMB temperature polarization, tells nothing, and then you have the supernovae, they tell quite a bit, I would say, right? And then the BAO, they are really also different. So it's really, a kind of combination of probes that works incredibly well for these two parameters. And they work also reasonably well for the neutrinos, in which you see that if you complement supernovae with the BAO, you get squash in this part of the parameter space in which you are consistent basically with 0. This is dark energy or neutrinos, but you can have also dark energy and neutrinos, like in this slide, another different paper. And in this case, the 2 sigma upper limit is 0.2 electron volt, which is remarkable, I would say. And again, you see, for example, this is omega neutrinos. You see that you have kind of the general C lines like this for the large-scale structure from Bose and eBose, and then you complement with Planck, and you get squash like this, a little bit like Lyman alpha. And the same numbers of Lyman alpha, 0.2 is more or less like 0.12, in my opinion, right? So when I was, at some point, I was presenting some neutrino constraints many years ago to an audience of particle physicists working on total mass of 1 electron volt. And I was saying that it was 0.12 electron volt. And they said, we don't believe your results because your model is cosmology dependent. If you change W, your constraints instead of 0.2, 0.1 will become 0.3. And at that time, it was true. It was becoming 0.3, even 0.5 if you also allow for curvature. Now we're not in that situation anymore. Now we have so many probes from different, sides of this parameter space that are entering and are really tightening things up. And so for particle physics, I guess it's going to be a hard time to go down to these numbers in a reasonable amount of time. Let me skip this. This was, to show that you can also have cross-correlation with the CMB lensing. These people did, and they get an upper limit of 0.14, completely independent people. This is somewhat going to scales that are more non-linear, right? So what do? They parameterize this F sigma 8 in this way, and this gamma F is a parameter that tells you the deviation from the lambda CDM value, right? And so what these people saw was the following, that basically they have these parameters, VBC, which is a parameter which controls the way in which you populate each halos, dark matter halos, with galaxies, right? You have the arcMOX, and you put the galaxy there, and this galaxy can have a little bit of displacement with respect to the center of mass of the halo. This is the way in which I see this thing. And they found that this correlates with this function here. So it correlates in this way, and this correlation depends on the scales. So what is this hinting at? It's hinting at the following thing, that basically, if you are brave enough, you can say maybe, it's a failure of my models in which I populate wrongly, right? Or maybe there is more mass in the halos to account for this misplacement. The HOD model is breakdown, maybe there is new physics, maybe there are systematic errors. And what you see here is this gamma F. You would like this gamma F to be 1, and it's 1 basically only for a subset of this probe. So if you want, it's the same thing that I showed before. It's essentially a modeling of distribution of matter at small scales compared to the larger scales, exploiting the Redshift space distortion at somewhat small scale. So here in this case, you are brave. You want to go down to scales of, let's say, 7, 8, 1 megaparsec, and look at how your clustering model compares to the data, right? And of course, this could have implication in terms of modified gravity. So Boss' main conclusion, 1% constraints on this, amplitude of peculiar velocity measured at the 10% level of better, no evidence for physics beyond lambda CDM, perfect agreement with Planck, also the H0 value that they infer from the full shape, as I will show you soon, is in agreement with Planck. Limits on the trino mass are in this ballpark, not even a support, which I haven't talked about for an F larger than 3. So there is no new physics, but maybe there will be new physics because we have DAISY taking data now, we have Euclid, we have FST, we have W1st Roman. So soon there's going to be a huge amount of data ready to take all this machinery one step further, right? In statistics, in systematics, and so let me provide you also with a connection with maybe some of you who are more theoretically oriented. This is a very nice paper by Philcox and Ivanov, in which they model in a completely independent way the same data set by using the effective theory of the large-scale structure, which is a perturbation theory. There are many around. This theory has gained a little bit more attention in the last few years, right? Also because notable people are working on this. And also they do two things. They use this theory. They also have a method to compute things which basically does not deal with the window, which is a problem, as I told you in the beginning. Is window free, they call it. And also, they use the bispectrum, right? They use this B0 as the bispectrum, so higher order, and this is Q0 is this term here, which is related to the monopole, quadrupole, and hexadecapole of the real space power spectrum. So it's a further constraint that they calculate out of the data and that they put into their machinery. Again, what do they get? They get very good consensus results by having this different data combination. This is the first result they get. They measure sigma 8, or better to say, in this case is capital S8, which is a combination of the two. The CMB measures this quantity, is a derived quantity. DES, as we will see tomorrow, measure this value, and instead they get this value by using the full shape information. Here they are not after the position of the peak. They also look at the peak, but they also look at the full shape, right? And they get this number, which is in agreement with this, a bit on the low side compared to Planck, I would say, because you see it's a kind of 2.5 sigma tension with respect to the CMB. In the case of DES, maybe it's a bit less or more. Well, we can talk about this tomorrow. So how this effective field theory works is relatively straightforward, at least to write equation down, maybe, and then computation gets a bit more contrived. You start from the Vlasov equation, you write the moments like this, and then you have the continuity in Euler. And now you make an ansatz for having a generic fluid with a given viscosity. The ansatz is this. And the key point in all this perturbation theory is to coarse grain, short scale and large scale, and to have, you know, an effective description of the two different regimes independent of each other. And to see whether the short scales can back react on the long scales. Right? That's the idea of all the perturbation models. And indeed, it's what also comes from the equation, in the sense that if you work these things out this way, you can write an effective stressed energy tensor, in which you see these S terms are referring to small scale quantities, and you plug this in, and this basically back reacts over the fluid at large scales with as if you had a fluid with an effective pressure, which can be written like this. There are many papers out in the literature. And basically, once you define the separation between the two scales, and you define also a range of validity, is basically you solve a equation, sometimes calibrated with n-body, and you let, you know, all of this compare with the data. So at the end, things are a bit more complicated, but they can be casted in more physical way, because you have a bias expansion terms, which has the usual bias, and then the higher order terms, which can refer to the tidal distribution, to the Laplacian density field. And so at the end, you parameterize all of this with some priors taken from simulation. And at the end, you see how many parameters that you marginalize over. And so this is quite prior dependent, of course, right? Might be. But what the point that I want to make here is that at the end, this approach is maybe based on more fundamental, let's say, pillars, because perturbation theory can be understood. These terms, they have physical interpretations. But at the end of the day, you're faced with the same problem as we were facing yesterday with the Lyman alpha forest. At the end, you have MCMC with 20, 30 parameters. You have to explore this parameter space fastly enough, and sometimes you're not fast, and get numbers. And these people, they got reasonable numbers that are, let's say, in agreement with other analysis. Again, future seems bright. Before I said 1%, in reality, some experiments are wishing to find the distance scale error below the 1%, so especially at high redshift. So this will really allow you also to explore, you know, the high redshift regime. Let me conclude. I'm done. So we leave time for questions. So of course it was a fast review, no? What you can do with galaxy clustering. There are many exciting questions to be asked. There are also many exciting approaches, right, to compare data and simulations, based on perturbation theory, based on MOX. I hope I showed you that, you know, MOX can be of several different layers of, you know, physical enrichment, right? In the sense it could be simple MOX, but then you can enrich them with more physical insights from simulation. And then the two main things is that galaxy cluster is going to probe geometry to the BO peak position, but also the shape, so of the power spectrum, not even looking at the BO peak, as these people did with perturbation theory, is going to provide us with information about cosmological parameters. I didn't talk about H0, even though it was probably shown in some plot, right? This H0 value here is in perfect agreement with Planck and not in agreement with Jueves. And they claim here there is just a prior on omega B, omega baryon, but nothing else is used, just the shape, omega baryon, and very few assumptions that they claim are model independent. So it's a powerful way of doing fundamental physics. Unfortunately for us, there is no new physics yet, but hopefully there will be. Thank you, I'm done.
Hello, thank you for a nice talk. Today you were talking about galaxy clustering, so about high density regions, and yesterday about Lyman alpha that probes low density regions. So I wonder whether it's possible to combine these two approaches, maybe studying cross colorations or something like that to obtain better results?
Absolutely, absolutely. Indeed, you know, when the Lyman alpha forest was, when people started to investigate the Lyman alpha forest many years ago, the first thing that they look at is whether or not there were galaxies nearby, right? And so, because they wanted to see, maybe because if there were, if at any Lyman alpha forest source there was a galaxy, they maybe, you know, they trace each other somewhat with different paths. And that was not the case, as I said yesterday, because you find Lyman alpha forest filaments even in voids, okay? So they are clearly independent environments. And the bottom line is, yes, you can combine them, you can do the cross correlation, but the point is that where we do have lots of Lyman alpha forest information, we don't have that many galaxies, right? Because you do have quasars, and indeed yesterday I showed that you can find the BAO peak also in the cross correlation Lyman alpha quasars, but so far we don't have that many galaxies. That will become routine maybe with the next stage 5 of spectroscopic, in which maybe even sphere X, I don't know, in which they will survey galaxies at redshift 3 and 4. But so far we have just small fields there. Lyman break galaxies, very bright and typically small fields. Yeah, but it will be important.
Yeah, thank you.
Hi. So I wanted to know, in the dark energy talks, we have been seeing that assuming a cosmological constant is a bit far from being such an agnostic assumption. So I wanted to know how much you think these constraints on the neutrino masses actually depend from this particular parameterization of dark energy, for example.
Yes, as I said, a bit less compared to a few years ago, in the sense that you see now in this case, let me see. In this case, you see you have W and omega matter which both vary, right? And this different data combination is really cornering you into this part of the parameter space. A few years ago, these contours were much larger. So in a way, you're right, we have to be a little bit more agnostic, right? But in a way, lambda is a solution. In a way, probably, in my opinion, sometimes I see lambda as even the most reasonable solution in the zoo of craziness of theories, which you know can. And so far, all you know, all the information is, all the data are pulling us into this part of W equal -1, right? And so, and there is not so much room to go from, let's say, 0.14 electron volt to 0.6 electron volt. You can go maybe from 0.14 to 0.25, but not anymore to 0.6.
Can I make a slightly different question? So you showed that these constraints on S8 have improved a lot using the EFT of LSS. And these rely on the extension to more nonlinear information, right? So I wanted to know how you weight the first point that you made, that improving the error bars on large scales would be determinant to measuring sigma 8, for example, with how much of this information is actually coming from the nonlinear part of structure formation, and how to actually improve these by extending into this small scale part of the spectrum.
Yes, let me see if I have. Okay, well, I don't have. I mean, for example, you see these people here. They don't use perturbation theory. They use a model of the bias, which is, let's say, which is simple 2 parameters. Here they cross correlate the Bose data with, they add also the cross correlation of the very same galaxies with the weak lensing. And what they do, for example, in terms of neutrino masses, is that by increasing K max, the neutrino mass, total neutrino mass gets stable. So that's their conclusion. So we know the neutrino mass is somewhat correlated with sigma 8. So my point is the following. If you add more modes, you are typically more constraining, okay? So if you add more modes. But typically when you add more modes, you need to take into account that these modes come with an expensive burden, which is the fact that you know how to model these modes a bit less well compared to the linear scale. So for example, a effective field theory of the Rayleigh structure could be the right perturbation theory, but there are several others. So when you start to bring in also, for the nonlinear modes, some conservative error bars, bracketing the theoretical models, but how you model these scales, you don't gain much. And so then it's really up to you. You want to be aggressive, you want to be conservative, stop at large scales, just use linear theory, then use some EFT that works. At some point, every EFT theory will fail. If you are brave enough, maybe an HOD will bring you even farther. Halo model can bring you even farther. It's a balance. At this point, I would say that the statement bringing in more nonlinear scales is going to help us in determining sigma 8 better. In principle, yes, but in practice, no. In the future, I don't know. But at this very moment, I'd rather use a conservative approach.
Thanks, Matteo, for the lecture. My question is, do you think it is possible to apply the same technique of pixel-based reconstruction to Lyman alpha forest instead of H1 intensity mapping?
So that's a good question. So let's put it in this way. For the 3D so the BAO are applied to the 3D power spectrum or 3D correlation function, right? In 1D, it's very difficult to see the BAO. But in 3D, you see them especially by having a transverse direction. And the point is that people, okay. I don't think there are many works on reconstruct. Actually, I'm not aware of techniques of reconstructing the BO peak from the Lyman alpha forest. Maybe for two reasons. One is that you are more linear at these rashes, and then you're also dealing with the flux rather than density. And the flux kills. It's also a nonlinear transform. So in a way, there might be an effect. People have not investigated it yet because the error bars of the measurement are still probably relatively large compared to the actual, better reconstructed peak that you can help you gain in a bit. Okay, but maybe it's a good point, right? That you can use pixels. In that case, you have pixels, right? You can move pixels, flux pixel, to gain a bit and sharpen the peak a little bit. That's maybe something to look at. Yeah.
Thank you very much for the lecture. I have a basic question on the beginning of your talk. So you mentioned that the two-point correlation function can be interpreted as the average density profile. And I wanted to ask you if you have, let's say, an intuitive way of seeing this. Because in my understanding, I would more think of it like as a second moment, so more related, let's say, to a variance.
It's given by this equation here, in the sense that if you start counting neighbors around you, this is the differential number of neighbors as a function of the distance. It is written in this way. Then you integrate this. By integrating this, you also integrate the correlation function, so it will be an average correlation function. It will become, and you really see that it can be interpreted as a profile, okay, as a density term around you. So that's it's a mathematical interpretation, if you wish. But the thing that you just said, what do you say, second order moment of the
of the density field
is also valid, right? Because yes, in this case,
exactly.
it's also the same. Yeah.
Yeah. So thinking of it like as the variance.
Yeah.
Thanks a lot. That's clear.
Okay. Hello, everybody. Just wanted to say before we start the third session that I really enjoyed the student lectures yesterday, and partly because it was really a pleasure to see you suffer the same torturing device as we do all the time. Okay, so third lecture, and what I'll be talking about, is beyond mean field effects. So I mentioned in the first lecture that most of what we see when we look at rotation curves, dispersion measurements, etc., of galaxies are essentially mean field effects. We measure the integrated mass inside of some region, or the mean Newtonian gravitational potential. And what I want to do today is to explore beyond the mean field regime and see what we can learn. And before I go into the main part of what I want to talk about, let me just make a short comment about a whole large field of research that I will not comment about, and that is the research of dark matter substructure. And it's really very broad. You can find many discussions in the literature. It's very interesting. Just to flash some examples, for example, lensing measurements can find magnification anomalies and other features that can potentially see if you have dark matter substructure as expected in hierarchical lambda CDM formation of structures. They can look for dark matter mini halos or very massive compact objects, stellar streams in the Milky Way and near the Milky Way, reaching very interesting precision. So these are examples for walks. There's several walks by Joe Bovey and others on this, also very promising. And then, of course, very high precision measurements of the 3D motion, basically the 6D phase space of stars in the Milky Way. This is new stuff. It's becoming available with Gaia mission, and you get full 3D mapping of the positions of stars and the accelerations of stars. That is also very promising, and I will say nothing about this in the rest of the lecture, not because I think it's not interesting and not new and exciting. It is all of that, but because I chose to focus on something slightly different. So the field is very rich. And to set the stage of what I will choose to focus on, let's look at Fornax again, this dwarf spheroidal galaxy. We looked at the dispersion curve of Fornax before, and what I put on the left is some example of dark matter models. So in this plot, there is density as a function of distance. These are mass models for Fornax. This is a model of the stellar contribution based on stellar evolution models and on the measurement of the brightness. But as you can see, we discussed this a bit before in the first lecture, there are several different, actually potentially radically different looking models of dark matter that can all fit reasonably well the observed velocity dispersion. Okay, so there are many degeneracies, and all of this analysis is a mean field analysis, and it has its limitation. So it's natural to ask, when we look at Fornax and other systems, are there any additional objects inside of Fornax, in addition to stars, and just the motion of stars, that we can use to learn something else? And the answer, of course, is yes. For example, Fornax and many other galaxies contains globular clusters. So here I highlighted 6 globular clusters in Fornax. One of them is a little bit controversial, but 5 of them are well established. And I'm zooming in on one of them. This is an actual zoom in. Fornax is very close. You can actually resolve individual massive stars in Fornax. And so this little dot, when you zoom in, you discover that it's not some very bright star. It's actually a conglomeration of stars in the ballpark of a few 100,000 of stars that are very closely tied together. They are essentially bound to the self-gravity of the globular cluster. And so as this globular cluster and his neighbors are moving in the galaxy, they behave like a very massive test particle that is moving around in this mean field. And it's natural to ask, can we learn something from this? And I mentioned also in the first lecture that, as we all know from high school, rhinoceroses and apples in a gravitational field, they move on the same geodesic. Well, this is exactly the counterexample. So an apple weighs in the ballpark of 100 grams. A massive rhinoceros is a few thousand grams, a few thousand kilograms. I can actually, this is my command prop on MATLAB, I calculate the ratio of the mass the ratio of the mass between massive rhino and a light apple is in the ballpark of a few times 10 to the 4. So what we have here, we literally do have rhinoceroses moving in a sea of potentially apples, sea of stars. But in fact, it's more interesting than this. These globular clusters don't just move in a sea of stars. Of course, we think for fornax that most of the mass in this object is actually coming from dark matter. So the massive globular clusters are moving in a sea of dark matter particles mostly. Stars are actually just a small perturbations on that. So if we can see, we don't actually know, if you want, we are covered, these rhinos are moving in a sea of black apples, we don't know what they are, and that's the thing we want to study and we want to understand from here. And fornax is just one example, and fornax has only 6 globular clusters, but lately, there is a lot of discussion about another type of galaxies that are called ultra-diffuse. They're not so different looking from fornax. This is also a dwarf galaxy, but they're even more diffuse than fornax is. It's like you take fornax, you take the same number of stars, and you stretch it by a factor of 2 or 3, so the density drops by a factor of 10. That's why these galaxies are ultra-diffuse. And the interesting thing about them for us is that they tend to host many, many globular clusters in them. So in this picture of this UDG galaxy, the black spots are globular cluster candidates. We think they're globular clusters. And if you look carefully, you see actually something interesting. You see that the big black spots tend to concentrate in the center, and the small black spots are more kind of distributed in the outskirts of this galaxy. So that's very interesting. We think these are globular clusters, and we actually think that the bigger spots are more massive clusters. We think that this spot, from its luminosity, has in the ballpark of 1 million solar mass in it. The smaller spots have a few 10 to the 5 solar mass in them, okay? What could this be coming from? So what I did here to study what this could be coming from, I'm just running an n-body simulation that you see. It's a 3D full n-body simulation. It's small. It has only about 30,000 particles, literally just solving the Newtonian equation of motion. Oops. And all the blue dots in the simulation you should think of them as stars or small stellar mass-like particles. Okay, these are the blue dots. Let me start it again. The red dots are globular clusters with masses that are typical of what we think the masses of the globular clusters in this galaxy is. And what I'm doing here, I'm letting initially the red dots start with a distribution in phase space that is identical to that of the blue. So the red dot starts with a distribution that is identical to the blue. But when I let the simulation run, as you can see, the red dots seem to in-spiral and fall inside. When they fall inside, they interact. These red dots are supposed to mimic globular clusters, and so I'm also implementing a prescription to tell me what to do if 2 globular clusters encounter each other slowly, so slowly that they have negative binding energy and they could merge. For this, you need a perturber next to them, but you have it, so some mergers happen here. And the interesting thing is, if you compare this picture from the numerical experiment to this picture, it seems to be suggestive. We seem to be seeing something here, and the effect that led the red dots to fall inside is a beyond mean field effect. It is a qualitatively different probe of what it is that comprises the mass profile of this galaxy. This is qualitatively different to just measuring the stellar dispersion of the blue dots, because this motion is actually coming from the massive red points interacting with many, many soft collisions with the blue stars next to them, losing energy and falling in. This is the effect that I would like to demystify, and this is the effect that I'm going to go after. Let's understand it. Now, so the effect of dynamical friction, I think it is very important. I think it is promising to tell us something new about dark matter, and I would like us to understand it. There is a very quick and easy derivation of this effect that you can find everywhere. I could also do it for you on the blackboard after the talk in 5 minutes. I'm not going to take this route. I'm going to take a different route. It is much less intuitive and more complicated, just violating any pedagogical rule that you probably heard. The reason I want to do it, however, because I think it's good to see a new derivation and to derive important things in many different ways. B, because I don't think you've seen this derivation before. It's likely that you haven't. And C, because it connects very directly to particle physics, to basic physics. I want to give you a particle physicist perspective on dynamical friction. It's not going to be too long, and I'm going to skip all the integrals. So we start with the continuity equation, and what we're thinking here is that we have two types of particle moving in a gravitational system, type 1 and type 2. Eventually, we will think of type 1 as being globular clusters, and type 2 as being dark matter particles. Type 2 are also stars in reality. There are more than two types. And what I'm writing is the continuity equation. Let's say for type 1, everything is going to be non-relativistic. This can be corrected, but you don't really need to. Everything is non-relativistic in these galaxies. Okay, so we have a continuity equation. As usual, what we do is take moments of it. There is information in all the moments. I just take the velocity moment here, and I get the equation that we saw before. And now I'm going to completely misuse this equation that I got. Again, just to provoke a little bit of thought, I'm going to take the distribution function f, and I'm going to use it to describe one particle. Okay? And it's a nice experiment to do, to understand what's going on. So what I'm going to say this f actually describes one particle of mass m that is very concentrated along this world line that goes through the coordinates x of t with velocity v of t. Okay, let's get equations of motion from the continuity equation. Why not? Okay, just think of distribution function that's sharply picked. I don't have to do all this. I do it just to make us think a little bit. And I remind of the normalization of things. So the density of my one particle is a delta function in space, right? So the integral of my distribution function is just a delta function along the world line, for example. Velocity will do the same. Now, because I'm using this awkward density, my continuity equation or Jeans equation looks a little bit funny. To get rid of all these silly delta functions, I just integrate over all space, and then I will isolate my particle. Okay? So let's do it. We do this integral, assuming that this object vanishes on the spatial boundary of the problem, as it will. What I have here is simply the usual collisionless equation, right? Acceleration is just equal to the force, which is minus the gradient of the potential. Okay, so this machinery, this funny machinery seems to work. But now let's get some more juice out of this machinery. First thing to point out is that what I really am going to care about is not collisionless continuity equation, but continuity equation with a collision term. This is going to be a collisionless collision term. It's going to come from the passages of particles in the background that are passing next to my test particle. Okay? So in my formalism, this is what I need to do, right? I took the velocity moment before, now I took the position integral. So therefore, this equation is going to be corrected by an integral over the collision operator. Great, so now the particle physicists are happy. They can simply calculate the collision operator. So let's calculate the collision operator in just gravitational scattering. We're looking at one graviton exchange. You can literally calculate the diagram. This is the matrix element for the diagram. I'm even going to have my target particle have spin s if I want. It doesn't matter. You can throw the s if you don't want it to have a spin. But this is the one graviton exchange matrix element. Q is the exchange momentum, right? So my particle comes in with momentum p, scatters off some gas particle, target particle momentum k. They go into p prime and k prime, and q is the exchanged momentum. And here is the matrix element. Now q0, at very low energy, the energy part is suppressed. So at very low energy, everything looks instantaneous, as you all know. And so this is going, you can work out the dynamics or the kinematics, but this is negligible. All you care about is the vector q. So that's the integral I need to make. I'm even being very judicious, and I'm keeping possible degeneracy factor here. I'm going to go back to this in the end. Okay? So I let even, I'm allowing this thing to have Bose enhancement or Pauli blocking, if you want, in the distribution function f1 and f2. And these are just the d3k, the phase space elements. Okay, so that's, I said this already. Let me just make one comment about this crazy derivation that I'm going to make. This derivation, the calculation of the matrix element, assumes three asymptotic states, right? I'm taking just plane waves of globular clusters, right, and stars. I'm sending them and letting them collide into three states with just momentum eigenstates. This is, of course, an approximation, the use of asymptotic states, because my particles are not free. They're moving in some halo, in some orbit. They care about the orbit. They're just very locally, closely looking like a plane wave, but farther away, they will not look like a plane wave. Okay, so this is one approximation that I'm making. I'm ignoring back reaction also. I'm ignoring how, I will ignore soon, how these collisions modify the distribution function of the target gas. And I'm ignoring non-trivial boundary condition. I'm ignoring, at this point, again, this is related to the fact these particles are moving in a halo. So basically, the density of scatterers is locally constant. That's what I'm using. So these are comments for the derivation I'm using. All of these comments apply to the usual derivation, for example, in the book by Binney and Tremaine, and in any other derivation you'll see in the literature. There's nothing new here. Okay, so I'll skip through this very quickly. What people usually do, they take your collision operator. I have done nothing here, just to split the three momentum integrals in this way. And this object that takes the K integral is called the response function S. You can stare at this later from my notes if you want. And one thing you should remember, again, you don't need to understand all the details right now, is that we're going to make a Fokker-Planck expansion. Fokker-Planck expansion simply means that the momentum transfer Q is much, much smaller than my typical transfer, or than my baseline momentum P, for the types of collisions that are going to be most important for us. This is certainly true if you have a globular cluster, a very massive particle moving in your halo, and it scatters off of low mass stars. This can be slightly less correct if you globular cluster, for example, if you want to describe stars being scattered by a globular cluster. Then this approximation could potentially fail, so it's good to keep track of it. If I do it though, I can expand my collision operator in objects that are called diffusion coefficients that are simply Taylor expanding the integrals in powers of Q. That's all they are. The first one is the first power of Q, and the second one is the second power of Q, and I could go on. I'll stop at the second one. And I can calculate, I'll pull this even a bit longer. So just with gravity, I wrote the matrix element before. Let's assume that these are just classical massive particles where the distribution functions are much smaller than 1. I forget for a moment Pauli blocking and Bose enhancement. And then I can simply calculate. These are famous results. And the objects on the right, H and G that you get, they are called the Rosenbluth potentials, just integrals over this Green's function for graviton exchange. That's all it is. You can just reproduce all of this doing the integrals directly. One comment I would like to make. These approximations are made before about asymptotic states. They map to what looks like a divergence in the calculation. This divergence is called the Coulomb logarithm. So you see, I've got an expression for this diffusion coefficient. It's a local expression that depends only on P, only on the momentum of my massive particle, and some integrals that you'll see soon of the distribution of the target particles. But in front of all of this local beautiful thing, there is some ugly fudge factor, which is this log lambda. And this log lambda, from our point of view of the matrix element calculation, is literally a divergent integral. It's an integral on Q that is logarithmically divergent, both at very large Q and at very small q. None of these divergences is very problematic for us per se. So at very large q corresponds to scattering at very short distances. All of you understand that q cannot really become very large because the momentum exchange, the maximal thing you can do, a particle can come to my globular cluster and scatter back. That's the most momentum you can ever give, or my particle, right? It can either go without scattering, it can make as many loops as you want, but the most it can do is scatter back. So there is always a cutoff at large q. That's not a problem at all. The cutoff at small q is more interesting. The cutoff at small q describes the fact that, in fact, this calculation, which I try to present as a local calculation, really logarithmically depends on collisions that are very, very far away from me. If I could exchange momentum, because the gravity only goes down like 1 over r, the potential goes like 1 over r, in fact, scattering many, many very soft scatterings with numerous faraway particles can dominate this effect. What physically cuts off this divergence? What cuts it off are several things. For example, very soft collisions from far particles take infinite amount of time to happen. The age of the system will cut this off. Also, if the system is finite in size, there are simply no faraway scatterers to scatter on. But the bottom line, you see that this divergence depends on boundary conditions. There is no way that in a local calculation I can capture the properties of this fudge factor. It's going to stay and annoy us more or less to the end, but there are ways to deal with it. And this fudge factor is there for any derivation and calculation of dynamical friction, not only this one. It's not special for us. Okay, so I can do this quickly. So we did this calculation. Again, this is what we need to do over the collision operator. We need to take its volume integral and moment. Our type 1 particles are globular clusters. You can simply take this integral over what we got before. Well, the integral over this piece, the momentum integral vanishes. It just doesn't contribute to momentum drift. But the integral over d1, the first diffusion, di, the first diffusion coefficient, this doesn't vanish. And it leaves you this factor outside. This is mean momentum drift. Had I tried to calculate not momentum drift, not the change to this equation, but drift in energy, and I would take a second moment, Vi, Vj, then this thing would survive and it would show energy drift. And in fact, this momentum, this diffusion coefficient is important. It's related by a fluctuation dissipation theorem to the first one. I'm not going to go into it, just to show that there is a lot of juice in this. There is a lot of information. Okay, so I can do the calculation. And all of this you can reproduce yourself. Simply doing the calculation, the integral over the Rosenbluth potential, I get this formula for the collision term. The object on the right is a relic of this Rosenbluth potential. Remember that what I have here, I have some integral over the phase space of gas target scatterers, right? So here is where the information remains. First, I'm sensitive to rho, which is the local mass density of the target gas. Okay, rho is the density of the gas through which I move. Second, there is this C coefficient, dimensionless coefficient. This is called the Chandrasekhar dynamical friction coefficient. And what does this C do? This C integrates over the phase space, local phase space of my target scatterers, and it counts how many target particles I have that are slower than me, okay? The velocity of this globular cluster is V, and now I'm counting the fraction of target particles that are slower than the globular cluster in the local rest frame of this object, compared to the total number of particles. Okay, so if the gas is very, very, very cold, this C will be 1. If the gas is very, very hot, particles move very fast compared to the perturber, this C will be close to 0. Okay? It's a beautiful result by Chandrasekhar. It only holds for an isotropic distribution function f, which I'm assuming here, can be easily modified, say, for this galaxy. But here is the point. If you stare at this formula a little bit, it looks like this. Okay? What I have here, V dot, the collision term looks like 1 over tau, some coefficient, times the velocity itself. Vi in component notation is just the velocity itself. Okay, so the equation actually becomes very simple, and here is what tau is. I'm just reading the coefficient in front. A local coefficient that behaves like friction. It becomes large. This negative, this deceleration term becomes large if my velocity v becomes large, up to the fact that there is this v cubed in front also in tau. Okay, this is due to Chandrasekhar, and again derived in many, many different ways. So we got it from the particle physics point of view. I'll refer to this in the end also. I will need it. Let's see how well it works. Back to the n-body simulations, and let's make a very simple simulation this time. Let's make a simulation where I just take one globular cluster and I start it on a initially circular orbit. And I want to see what it does. And what it does is that it spirals. And it spirals essentially solving this equation. Here there is no fudge factor, there is no nothing, there is no Coulomb log, there is no nothing, right? Coulomb log is being imposed by the physics, by the actual size of the galactic halo I'm using, and by the size of the cluster. And what you see on the right, I make this plot that tracks my particle. On the y-axis, I plot the radius of the circle divided by the initial radius. This is time. all the colorful lines are results of separate realizations of the full n-body simulation. The green lines are very small simulations with just 5,000 perturbers. And the red lines have 20,000 perturbers in this particular case. Okay? And what you can see, they all follow the same interesting trend. The orbit decays down, there is noise, and the orbit stabilizes eventually at some radius. And it's interesting, you can see that the noise decreases when I increase the number of particles in my calculation. This noise is related to additional contributions to the diffusion coefficients that I have neglected when I took the limit that the mass of the globular cluster is infinite compared to the mass of the target particles. And the coefficients are still, these terms are still there in my limited n-body simulation. But the trend is fine. And what I show in the black line is a simple direct solution of this calculation. And the reason, so you can see the trend is essentially correct. There is a small difference in the slope. And this difference in the slope is because I intentionally didn't try to kind of fudge calibrate my fudge factor, the Coulomb log. I used some simple equation to define the Coulomb log. The point in mind is that, of course, I can take simulations and calibrate this black line, and I will capture the correct effect. So this formula really works rather well and can easily be calibrated if you have an actual system to study. So you understand dynamical friction now, I think. And we can see what can this tell us about dark matter. So the first thing we do, we're physicists, we're going to take this formula and put numbers and apply it to actually things we see in the sky. So let's apply it for Fornax, for GC3. I apply it for Fornax, I simply plug in the value for the density from a plot like this, for example, and I know the velocity of this globular cluster to some extent, at least the projected velocity, and I can get the gist of what this coefficient is. And interestingly, the coefficient in front is much smaller than the age of Fornax or of the globular clusters in Fornax. It's in the ballpark of 2 or 3 gigayear for this globular cluster. What does it mean? It means that naively, if this globular cluster actually experienced dynamical friction as expected, it should have actually inspired somewhere close to the center of Fornax in a time that is much shorter than the age of the universe. Okay? What's going on? That's quite interesting. In fact, this point related to the globular cluster in Fornax has a name. It was called the globular cluster timing puzzle. First, I think, discussed by Scott Tremaine in the 70s when he used the lattice formalism of dynamical friction to understand galaxies and globular clusters, but discussed all the way until today quite heatedly, and there is no clear consensus as for the solution. However, is this a problem for cold dark matter? Is it not a problem for cold dark matter? It is not so clear. The thing about Fornax is Fornax only has 6 globular clusters. That's not enough to draw any statistically significant conclusions, or at least it's very hard to convince oneself that this is very important. But then Fornax is just one system. We have dozens, maybe hundreds of systems that we can look at. And for example, in 2001, there was this survey that looked at 50 or so dwarf galaxies in the Fornax and Virgo clusters. It did a simplified analysis. I'm not going to go into all the details of that. But it tried to do exactly what I was showing here before. It essentially was asking, consider a galaxy and count how many globular clusters you see, estimate the dynamical friction time, and ask yourself, how many of these should have already fallen to the center, merged, and made what is called a nuclear cluster. Nuclear star cluster is just a name for globular cluster that merge or for a bunch of stars in the center of the galaxy. Well, these globular clusters should have made some nuclear stellar clusters. And again, without going to the details, the conclusion here was that there seems to be a shortage of these nuclear clusters. Okay, we see a lot of galaxies with a lot of globular clusters that should have fallen, at least in many of them, should have fallen and made a nuclear star clusters. And where are these nuclear star clusters? Okay, so they should have been here. We should have seen many more nuclear clusters. So is there a problem? In fact, this is reminiscent maybe of Fornax. Okay, this could really tell us that there is something very interesting going on. Maybe dynamical friction isn't working. Now, at least for me, this is super interesting because you think about dark matter. What is it? We look at galaxies. We count how many stars they are. We try to use Newtonian theory to tell us how fast the stars should move, and it fails completely. Okay, mean field fails. This failure we call dark matter in the context of galaxies. So now we have something else. We try to use Newtonian theory beyond mean field. Maybe it fails again. Maybe this time it fails in a way that what we call dark matter can't explain. Or maybe we can learn something. So I'm not sure. There were many simplifying assumptions in this analysis. It should definitely be redone. But there is much more data and more modern data, like these ultra-diffuse dwarf galaxies. And let's go back to our diffuse galaxy here. It has a huge amount of information, at least 30 good candidates for globular clusters. What can we learn from this, from the fact that the massive one seems to be in the center and the light one seems to be outside? Let's do it quickly, but quantitatively, okay, in just 1 minute. So what physics can we get out of it? So for example, you remember in the simulation, if I start the cluster on a circular orbit, it stays close to a circular orbit for a long time. It inspirals, but at any point along this spiral, the motion is very close to circular orbit. Okay, we can try to use this approximation. So if you take the equations of motion and consider orbits that are nearly circular, just to make our life simple, to get some simple estimates, then, in fact, you can get rid of the angular equation of motion. You're left with a radial equation of motion that you can present like this. So we have just an equation for the radius of this spiral. This equation I can just solve parametrically, presuming that I have a model for the mass distribution, essentially dark matter distribution in the galaxy. So let's call alpha the log, the slope, basically, of the mass distribution. Okay, so if the mass distribution is an NFW profile, this alpha is going to be 1 in the inner part. If the mass distribution is a core, this alpha will be 3. Whatever alpha I have, I can simply invert this equation and get an equation. If you tell me where a globular cluster is today, then I can, and you tell me where it started from, I can tell you how long it took for this inspiral to happen. I can just invert and solve. Let's push this a bit more. Suppose, for example, the dark matter, we think that the dark matter distribution in fornax and other galaxies is a core. If the distribution is a core, the Chandrasekhar tau is close to a constant, alpha is close to a constant of 3, and I can just solve the equation. And the initial radius is exponentially related to the final radius. The exponential is the dynamical friction time and the age of the system. Okay, let's map to what we see. What do we see? We are counting globular clusters at any given mass as a function of distance from the radius. So what we have a count n at the time delta t, say 10 gigayear, of how many globular clusters there are inside of radius r. Okay, this is the cumulative count going out. So this cumulative count relates to the initial cumulative count, to whatever the count was 10 gigayears or 5 gigayears ago, by this exponential transformation. That's what our calculation told us. And so we can ask what we really see. We see the projected distribution. So if we have a globular cluster, we see it over here. We just have the projected radius. So there is a little bit of a projected calculation to do. We can calculate, for example, the mean projected radius of the cluster. This is, of course, an abuse of notation because this picture is already projected, but I think it helps you understand what's going on. I can see what an integral like this boils down to. So if you change integration variables and use this relation, you immediately find out that the projected mean distance of the clusters from the center of this halo today is related to the projected mean distance 10 gigayears ago, of course not observable, some property of the initial distribution, exponentially like this. Take the log, you get this equation. Here is a 0th order prediction of dynamical friction, but it allows us to check quantitatively what's going on in here. And here is this galaxy, literally calculating and plotting the projected radius. So what I have here on the y-axis is the mass, essentially the luminosity of these globular clusters. So the very massive clusters are those guys, and the low mass clusters are the dots outside. On the x-axis, I have log of the projected distance on the sky. And what you see is just a mathematical or more quantitative presentation of this picture. The massive clusters are at small radii, the low mass cluster at large radii. The slope seems to be linear on a log scale. Okay? The reason that there is this slope is in the picture of dynamical friction that the friction time is inversely proportional to the mass of the perturber, to the mass of the rhino, right? The more massive the cluster is, the more effectively it decelerates. So this could be the first ever, to my knowledge, I would call it hint, or maybe stronger word, evidence for dynamical friction in a dark matter dominated galaxy, okay? This calculation and this result has nothing to do with mean field analysis. This is purely beyond mean field effect. It's a completely independent probe of dark matter compared to velocity dispersions. There are many, many related work, and I think it will grow a lot, because I really think this is a new window. Let me just comment, there is one big difficulty that may destroy this whole attempt, or maybe we can cope with it. The problem is, of course, we don't really know what was the initial distribution of clusters. We know what it is today, we don't know what it was initially, okay? So we need to somehow break down the degeneracy between where the cluster was 10 giga-years ago and how much dynamical friction is effective. So why do I think that there is evidence in this galaxy for dark matter compared to, say, only stars in the galaxy? This was a question for this galaxy initially. Well, the reason is that if there were only stars, dynamical friction is in fact much more efficient than it would be if there was mostly dark matter in the galaxy. Because dynamical friction is efficient, then in a model of a galaxy that has no dark matter, globular cluster must have started very, very far, 10 giga-year ago, to end up so squished the way we see them today. If the galaxy is dark matter dominated, globular cluster can start pretty close to where we see them today. The effect is there, but it is quite subtle. It is in terms of this mass segregation. Let me illustrate this with a short simulation. So what I'm showing here is a simulation that is going to of a galaxy like the one you've seen, that is going to demonstrate the effect. So on the right, I'm showing only the globular clusters without the target particles, and we're simulating them for about 7 giga-year. The dashed line is the mean projected radius that the clusters had when we started the simulation, and the solid line is the mean projected radius that changes as time goes by, and dynamical friction causes it to shrink. Here is what I have to do for this galaxy if there is no dark matter in this galaxy. I have to start globular clusters very, very far out compared to where they are today, and fine-tune this initial condition so I don't completely overshoot the positions of the cluster today. Okay? So essentially, the fight that this program is going to have is between the possibility that dark matter is dominating what we're seeing and the possibility that initial conditions somehow contrived to produce final distributions similar to what we see. And one recent work that came out just now at different galaxy, again, a very similar analysis. Of course, they plot wrongly the x and y axis. They should have inverted it, but they were impolite. But if you invert it in your mind, it's a very similar phenomena. And so according to these authors, in this particular galaxy, not only do we see potential evidence for dynamical friction, but moreover, we may see significant evidence that dark matter is really cored and not a cusp. We were more careful about this statement. I think there is still a lot of room to be careful, but this is promising. And as I said, there are going to be dozens, if not hundreds, of galaxies in which we can check this calculation. In fact, the local group here at the IAC is very active on identifying and studying globular clusters and diffuse galaxies. And I think they will have a lot to say about this problem in the future. How much time do I have? Okay, great. So there was a reason why I went through this particle physics derivation, and here is part of the reason. Let's discuss some example, fundamental physics example, how this can become really interesting from the fundamental physics point of view. Let's discuss this ultralight dark matter hypothesis that I talked about the last lecture. So as we discussed, it was thought for a while that maybe Fornax and many other galaxies are essentially ground state of this ultralight dark matter particle. And so what if my apples, the dark matter particles, are ultralight when I do this calculation? What funny things can happen to this dynamical friction calculation? The answer is that there is a funny thing and very interesting that happens. For example, here I have the Bose enhancement factor that I mentioned before in the collision operator. And this actually goes down into the calculation of the diffusion coefficient. I can still use Fokker-Planck approximation, but I have degeneracy effects in the calculation. Once you take these degeneracy effects into account, you actually reproduce, by the same matrix element derivation, results that are already known from an independent calculation of dynamical friction with ultralight dark matter. Interestingly, you find a phenomena that is called dynamical heating. It is essentially a result of Bose enhancement. And what it does, it shows you how the target particles actually clump into very massive clumps that actually act as if they were massive particles. There is a beautiful paper by this team with Scott Remain and postdocs at IAS, where they fully formalized this analogy. So what they do in the calculation, they take the density field of ultralight dark matter, here from a simulation by Luca Teodori, who's sitting here. And you can see, we talked yesterday about the core feature, but if you look outside the core feature, you see all these fluctuations in the density. Well, there is, in fact, an exact mathematical equivalence in the dynamics between these fluctuations and the presence of quasi-particles. These fluctuations act like bunches of mass that are traveling in the halo, and they are, in fact, very massive. They can contain a lot of mass. This is the analogy. The effective mass of this quasi-particle is proportional to the de Broglie wavelength to the cube, and the mass of the particle. Basically, the size scale of fluctuation is the Broglie wavelength times the background density, which gives you the normalization of the mass. So our stars and globular clusters are actually moving not in effectively a sea of these ultralight harmless particles, but because of Bose enhancement, they are moving in a field that is fluctuating and has a lot of thermal energy in it. And so this leads to dynamical heating. And actually, there are claims today of very strong constraints that people have derived on ultralight dark matter based on this dynamical heating phenomena. This paper, recent paper by Dalal and Kovstov, claims actually that ultralight dark matter is ruled out all the way to some 10 to the minus 19 electron volt, based on a particular star cluster in a particular dwarf galaxy that would have been dispersed by this dynamical heating formula that we could have gotten from the second diffusion coefficient that I wrote. It's exactly equivalent. Okay, so in fact, at 10 to the minus 20 electron volt, the effective mass of the fluctuations are at the level of hundreds of solar mass. That's how massive effectively our ultralight dark matter behaves. Okay, that's, if this constraint is correct, it is very, very strong. Here is an amusing fact. The exact same physics has been used to put constraints on macho or primordial black hole dark matter. Okay, that's a paper by Timothy Brandt, also was at IAS at the time, where he puts a constraint on the mass of primordial black holes or machos, and the y-axis is the Rayleigh abundance, the fractional contribution to dark matter, from star clusters in dwarf galaxies. It's exactly the same physics. Instead of quasi-particles, you literally have supposedly massive dark particles, massive apples flying around and hitting the stars. That leads me to an hypothesis, which is that if you go far enough to the extreme right, you find yourself in the extreme left. Anyway, so these are the macho constraints. This is the ultralight constraints. They actually connect. I don't know if I'm allowed to do things like this in a school. Never mind. A comment about this analysis. This analogy between, say, black holes and ultralight dark matter fluctuations does have a limit, of course. This effective theory breaks down at some, if you try to probe the system on small scales. The point is that the length scale, the de Broglie wavelength for these quasi-particles is not so small in the region of masses that these authors are considering. It's in fact, for this galaxy, at the ballpark of 100 parsec. Now, this particular system is tiny. I put this size of fluctuation in comparison to the star cluster itself. In this limit, you cannot use just the plane wave approximation that I've used before. It breaks down. It can give you an order of magnitude idea. Probably, it demonstrates the possible sensitivity of systems like this to ultralight dark matter, but one should be very careful when you apply it, because quasi-particles are huge. They're larger than the system of stars that they're moving. If you want, the Coulomb log is not under control in this problem. In fact, if the de Broglie wavelength is much larger than the size of the cluster of stars, then you run into a totally different scenario that really isn't captured by this matrix element calculation. In fact, you have to deal with coherence, full coherence of the distribution function of the gas. That's again for ultra-light dark matter. So remember, it was thought that Fornax itself is entirely inside of this kind of a soliton, a coherent ground state. If that was true, in fact, you can show dynamical friction is highly suppressed. Why is it highly suppressed? It's highly suppressed. This is a nice paper by the Princeton group. And it shows basically the wake field that is produced inside the ultralight dark matter soliton due to the motion of a massive point particle that is going in the soliton, right? So the particle is going in, it's making a wake. By the way, this kind of wake calculation is completely equivalent. You can derive dynamical friction through that as well by just solving the field equations. Well, if the scale size of the wake is much smaller than the coherence scale, the de Broglie wavelength, then you simply cannot excite it. You cannot excite the field to possess structure on scale that is much smaller than the Broglie wavelength. So this thing is non-viscous. It's basically there is no dynamical friction if you move through it on small enough scales. And so it was actually pointed out by Hui and by others that perhaps this suppression of dynamical friction is the solution for the Fornax timing problem. So if you want another independent possible smoking gun for this model, okay, if this was true. Unfortunately, as we discussed, and also Matteo mentioned, there are now strong constraints from other systems on this ultra dark matter. If these constraints are correct, the soliton cannot extend to the radius of these globular clusters, and it's irrelevant for the problem. But just imagine that it was. We could have seen it in yet another completely independent way. Let's go to the other point, Fermi particles. We discussed bosonic ultralight particles. What if dark matter is a light fermion particle? Again, there is something interesting going on. In fact, it was also suggested by some authors that dwarf galaxies and their typical scale, they could actually be some kind of white dwarf stars, if you want, degenerate solutions, if dark matter is fermionic and if it is light enough. Then you could again produce chord profile, and now the galaxy is supported by degeneracy pressure. And you can calculate, you can estimate what is the mass profile should be, and they're not inconsistent with what we see in ultralight dark matter. So let's go beyond mean field and try to understand what dynamical friction can say. And again, it can say something really interesting. Now we have Pauli blocking. We have some really interesting microphysics, because as my probe particle is moving through the gas, in fact, it is going to encounter, remember, only slow target particles are important. If you remember the Chandrasekhar integral, I only care about slow target particles. But if the slow target particles are deep in the Fermi sphere of this degenerate dark matter blob, you cannot scatter them to nearby states, because nearby states would be already full. So there is suppression of dynamical friction by Pauli blocking. You can get it directly from the calculation. It doesn't end up being so dramatic, but it does something very interesting. The classical gas result for the Chandrasekhar integral is that the Chandrasekhar dynamical friction coefficient scales like the velocity of my probe cubed divided by the dispersion of the target gas cubed. That's for classical gas. For the Fermi gas, this is replaced instead of sigma cubed. There are different numerical factors, and what you have is the Fermi velocity cubed. Okay? Basically telling you that you only scatter on particles on the surface of the Fermi sphere. You can work it out. It was also worked out for neutrinos in other contexts. Unfortunately, this cannot be relevant for Fornax. There is an easy way to show that it cannot be relevant for Fornax. Again, what we need for it to be relevant for Fornax is that these cores encompass the orbits of globular clusters. However, the mass range you need for this degenerate dark matter of order 200 electron volt is completely ruled out. The reason is it's ruled out essentially by cosmology, or among other things, by cosmology. The point is, in the early universe, such light fermionic dark matter essentially has to be degenerate again, because in the early universe, if you basically go back squeezing the proper volume, the density of dark matter increases, the number density, and eventually you're going to hit Pauli degeneracy again, and which means that your dark matter is necessarily going to be hot because it's essentially going to be at the Fermi speed. And so you can calculate what the gene scale for this kind of fermionic dark matter, and it actually follows very, very well the gene scale of velocity dispersion of warm dark matter. There is a one-to-one mapping to what constraints on warm dark matter say, and in fact, so what I'm plotting here, the green and red curves are constrained, or are the velocity dispersion as a function of redshift for warm dark matter. The red is 1 keV, for example. And the dashed curve are the minimal velocity dispersion for fermionic degenerate dark matter of 500 electron volt, a factor of 2 beyond what these authors thought. And so this is very well ruled out, and there is no way. So once again, these cores, if they exist, they could be stupendously interesting, but they have to be very small. They're not interesting for dynamical friction. Okay, I think I'm finishing on time. Thanks very much. To summarize, just in pictures, it's a very large field of research to try to understand constraints from beyond the mean field effect. I think there is a lot to look at every system. It's interesting now to go one step beyond and try to understand what's going on. And I should mention also in my first slide that there is a whole other branch of research related to substructure that I didn't talk about, but it follows similar reasoning. Thanks.
Thank you for a very interesting lecture. As far as I understood, your dynamical friction coefficient depends only on the mass density, not on the number density and mass independently.
Correct.
But in like classical hydrodynamics, in some low velocity regimes, we can disentangle number density and mass. So I wonder if we can find some wild non-mean field observable that will somehow disentangle number density and mass of dark matter particles.
Very, very good question. I would say so. This degeneracy, the fact that you're only sensitive to the product of number density times the mass of a particle, this comes up only at leading order in the expansion in the ratio of the mass of target particle divided by the mass of the probe, and for classical gas. In various ways, this approximation breaks down when you break these degeneracies, and it actually can break down also in a very tricky way. So for example, for the ultralight dark matter, in a way it breaks down because the effective mass becomes very different from little m. And so I would say the answer is yes, ultralight dark matter is one example. Possibly we can think about additional examples, but yes, so this degeneracy is really a classical result. I don't think it was explored very deeply. Can you try to somehow prove that you're sensitive not just to the local density, but something else? It could be interesting, and I don't know.
Yeah, thank you.
Hi, thanks for the very nice talk. I have a very basic question to see if I got the idea right. So you had a plot where the radius was decreasing as a function of t, basically as a Wiggly function, right? The idea here is that we have a dissipation, and associated to that there is always fluctuation, right, from the fluctuation dissipation theorem. So are the wiggles like the intrinsic noise associated to the dissipative process?
Interesting question. The dissipative process is not directly related to the wiggles. You're talking about the noise kind of that was seen in the numerical simulations. This fluctuation, so the wiggles, the fact that you see them so pronounced in the calculation, the numerical calculation, is because of breakdown of this continuum limit, because of breakdown of this, the first order approximation in little m divided by big M. This is the result of the wiggles. What you're actually seeing by the wiggles, you're seeing the effect of rare kind of head-on strong collisions with the target particles in the globular cluster that are stronger than they become more effective in the numerical simulations because the target particles are quite massive. That kind of sources the wiggles. The basic structure of the wiggles is because this is what the stability, if you check the stability properties of a circular orbit, and you ask what happens to the orbit if you give it a kick in any direction, you produce this kind of wiggles. You go down, then you go up. You basically, this is a 3D thing, I'm just projecting it, so it's a bit hard to see. So these are really the wiggles. Fluctuation dissipation theorem applies in the continuum, completely irrespective of the wiggles. So essentially the wiggles are not exactly this, not the wiggles that you saw. They are just related to the stability properties of circular orbits and the limitation of the numerical simulation.
Could I ask a short follow-up? So then in the case of ultralight dark matter, the enhancement of on the effective mass of these particles is related to the breakdown of the continuum limit in a sense, right?
Yes, absolutely. It is related to an effective breakdown of the continuum limit, and you can see it by non-vanishing second diffusion coefficient terms that are interesting, and also by surprising positive sign terms in the first diffusion coefficient that suddenly occur when little m is effectively not small. Yes, and it will also manifest in wiggles. So if you want, orbits in ultralight dark matter background are going to be noisy. Orbits in NFW CDM profile are going to be smooth, similar to the continuum limit calculation that I see. If we can somehow exploit the smoothness versus wriggleness properties, we can learn a lot. I'm not sure how to do it, because of course what we see is just one time snapshot of the system, right? These globular clusters in Fornax, the circle time is of the order of mega years. We just see one snapshot of this.
Okay, thanks very much.
Hello. I wonder if it is possible to estimate the dynamical friction calculation using globular clusters in the halo of large galaxies where the gas also is diffuse.
Absolutely. Thanks very much for the question. So in fact, much of the interest in this phenomenon of dynamical friction actually started in the context of massive galaxies. Galaxies like the Milky Way, Scott Remain and others were trying to understand if in the Milky Way, where we do see a massive nuclear star cluster, could it be that this came from accreting globular cluster because of dynamical friction? The answer they got was yes, but there are more questions you can ask about this, so the debate went on. So for example, you can ask, if you made nuclear star clusters from globular cluster, then the chemical and age properties should be very similar. However, in the Milky Way, the nuclear star cluster also have young stars in it. They don't look like they came from an accreted globular cluster, so there must be also some local star formation. So this is to show, so there is debate about this. Probably it's half and half, roughly, for the nuclear star cluster. This is just to show that massive galaxies might be complicated settings in which to test these ideas. Maybe systems like ultra-diffuse galaxies, or if I can find any galaxies with relatively coherent age distributions of globular clusters and stars, these might be more promising to test what we are seeing. But yes, it was used on massive galaxies.
Okay, so thank you, Ekfir, and thank you also, Matteo, for the talks. Now we are heading for lunch. We're not coming back this afternoon to this room, so basically we're locking it and until tomorrow. So if you have your things, please, and then we can meet in the gate at maybe 3:20. So we organize the two groups, and we can tell you where to go for the tutorials. Okay. Thank you.